Robots can learn from examples, but understanding how a demonstration works and what kind of abstraction can generalize from the demonstration is still a hard problem. Our work, Abstraction Refinement-guided programming synthesis, tackles this challenge. In robot learning, the goal is to produce a controller that drives the robot for task achievement. In this weight-solving example, at time step t, the robot observes the current environment state as t. The controller correspondingly computes the control action at to move the legs of the robot within the environment. Then the environment evolves to the next state as t+1. At each step, the environment also gives back a reward signal, RT, to feedback the controller. The objective is to learn the controller that maximizes the rewards the controller can receive from the environment. Deep reinforcement learning has emerged as a promising solution to this problem because due to its ability to learn controller without needing to know a model of the environment. Program synthesis for robot learning substitute programs in domain-specific language for deep neural networks. The benefit is twofold. First, programs are more interpretable. The learned decision logic can be read by the engineer. Second, programs are more generalizable. The same program can be deployed to mazes of various shapes alike. But traditional deep neural networks typically can only be learned and applied to environments of a fixed structure. There's a large amount of related work in programming synthesis for robot learning. Generally, a synthesis algorithm takes as input the robot environment, its reward function that gives a reward of 1.0 to task achieving states, and 0 for all the other states. Optionally, task demonstrations and a domain-specific language from which programs can be derived. Now the goal again is to generate a program whose execution maximizes the reward that it can receive from the environment from all possible initial states. So what does the DSL look like for robot learning? Assuming object-centric view, DSL variables refer to objects within the environment. In this pick and place task, for example, mu for the end effector of the robot, and then b for the block on the table. We assume a Go function g that maps environment objects to their target positions. The robot is expected to rearrange the objects within the environment to satisfy g. The DSL also include expressions such as projecting variables to their attribute, such as 3D coordinates within its workspace. And for computing relational quantities, such as delta y, the vertical difference between the end effector mu and the block b. The DSL includes basic functions, such as norm for describing object spatial relationships, and arctan2, which is useful for describing their physical orientations. The DSL includes event detectors, such as near, for checking whether the end effector mu is close enough to the block B. Those event detectors must be grounded using well-defined state abstraction predicates. Now here, phi is just a learned constant. The DSL also includes abstract actions, such as moving the end effector mu to any position within the 3D, within the workspace. Those abstract actions also need to be grounded using low-level policies, such as deep neural networks. The DSL also includes standard control structures, such as loops and conditionals. The main limitation of existing approaches for programming synthesis for robots is the reliance on handcrafted state and abstraction predicates. Handcrafted state abstraction predicate and also abstract actions. for something as simple as this pick and place task, that means defining state abstraction predicate for defining the robot, the end effector holding the block, or the end effector is moved above a block B, and also including actions such as opening and closing the grippers, moving the end effector up and down. So if you switch the synthesis algorithm to another domain, so those predicates and the abstract actions have to be redefined, which is not going to be scalable. So the research question we ask in our work is, can state and action abstractions be automatically inferred as part of the synthesis procedure? Our solution to this question is using abstraction refinement to automatically learn the necessary abstraction. And we call our method RoboScribe. So I'll describe RoboScribe through this block stacking example. So here the task complete condition is that all the blocks scattered on the table are formed into a tower. And finally, the robot arm moves away from the completed tower. To my knowledge, there's no existing deep learning algorithm capable of solving this task with a high success rate without assuming any domain knowledge. So in RoboScribe, the initial abstraction we constructed from the environment is simply true arrow CR, where CR encodes the task complete condition. So this abstraction means that we assume a single neural controller can be learned to rearrange the objects within the environment to satisfy the task complete condition CR from all potential initial states. The initial program, P-tower, takes as input the robot end effector mu, typed EE as input. So in this program, we expect this neural controller pi theta, which is used to ground the abstraction that can move the end effector until the task complete condition CR is met. However, from the execution of the learned policy, we know that just simply moving around the end effector all over the workspace cannot magically form a tower. Assuming access to demonstrations on how expert would perform this task, RoboScribe contrasts what went wrong with what went right. So this means that it learns by classifying states over failed program execution trajectory with the states just before success in the demonstration to learn what prerequisites are truly necessary to enable task success. In this case, it learns a classifier predicate at that captures an important subgoal. At least some block B1 has to be placed at its goal position. Here, the VC1 is also just automatically learned as a constant. Then we refine the initial abstraction by decomposing the whole task. The program from this updated abstraction gets some block from the environment and then use a neural policy pi theta 1 to tries to move the end effector to the end effector to move one block to the goal condition. And then it uses another neural policy pi theta to complete the rest of the task. In program learning, we deploy the robot onto the program onto the real environment, allowing each neural policy to gather experience in a replay buffer and apply standard reinforcement learning algorithm to improve the neural controllers to satisfy their goal condition. However, we didn't see any improvement. The neural policy pi theta 1 still struggles to place one block onto its goal position. Don't worry, we can continue run this abstraction refinement, which we call comparative abstraction refinement, And this time, we compare the states over field trajectories with the states in the demonstration just before sub-goal success in the demonstration. So we learn another important sub-goal predicate, hold. That means we need to first grab one object before trying to place it onto the goal position. Then we update we recursively update the initial abstraction, and in this new the new program derived from the updated abstraction uses a neural policy pi theta 2 to first grab an object, and then use pi theta 1 to move it to the goal position, and then use another neural policy pi theta to handle the remaining objects on the table. At this time, the program is able to at least put one block onto its goal position. Through comparative abstraction refinement, we realized that we can use the on-the-fly learned predicate at to put another predicate to refine the abstraction, which means that other than placing B1 onto its goal position, there's another block B2 that has to be moved to its goal position. We mark the predicate at as a circular node in the abstraction. This means that the control strategy learned for one block should be and can be generalized to handle the remaining blocks on the table. So we derive a while program that iteratively hold one block and place it onto the goal position. And then the final policy pi theta after the while loop only needs to move the end effector away from the completed tower. RoboScribe also fill in the loop guard to generate an object ordering predicate to determine the order in which the object needs to be handled through the loop iterations. We also learned this loop guard by contrasting states in the from demonstration by constructing state where a block is handled from state where it's not. The learned loop guard means that at each loop iteration, the program needs to select a block which is not positioned at its goal position, and second, all the block underneath it has been placed correctly to provide support. And then we deploy the program onto the robot and let the neural policies to generalize across loop iterations for all possible blocks. As a summary, RoboScribe can be considered as an iterative alternation between comparative abstraction refinement and program learning to construct the necessary abstraction for robot programming synthesis. So we deployed the program into this Tower 5 environment and find that it learns well. There's a quick jump in the success rate, and this is because the final policy to move away the robot arm can be learned quickly. After this skill is learned, the success rate quickly jumps. And we compare this with some baseline algorithms and find that RoboScribe is able to generalize the program learned for stacking 5 blocks to stack even more blocks, such as 8 blocks and 9 blocks. And also the program can be deployed onto new unseen tasks, such as stacking blocks onto a pyramid, where the baseline algorithms cannot complete the task. In the paper, we also describe environment. We also conduct experiments on more complicated environments and compare it with learning from demonstration baselines and find that RoboScribe is currently the best algorithm in this domain for task generalization. In conclusion, this talk, we present the comparative abstraction refinement as a general principle for constructive representation learning for synthesis. And we also present RoboScribe as a novel synthesis algorithm that automatically discovers the abstraction required in a DSL for synthesis. Thank you.
Okay, let's thank speaker. Yeah, you can sit up.